Starting recording. What we're going to be doing today is we're going to be looking at vertical projectile motion. Now, I was actually very surprised to see the number of people who struggled with vertical projectile motion when you filled in the form. Because I must be honest, vertical projectile motion for me is one of those easy sections. Yes, on occasion, they give you one where you've really got to think hard and you've got to have ups and downs and variables and simultaneous equations. But other than that, I find that it's a very straightforward section. So it did surprise me a little bit to discover how many of you really struggled with it. So before we get into it, I want to make sure that I'm answering and assisting you with the right things. So I want to start off by saying, who is scared of vertical projectile motion outright? Is there anyone who doesn't like it as a section? Okay, so it doesn't matter what it is, vertical projectile motion is not my friend. Okay, so quite a couple of you, but not too many. Okay, then the next question is, who is aware of vertical projectile motion being a challenge when they ask difficult questions involving simultaneous equations, and that's where it becomes a problem for you? Okay, so typically where it becomes a problem for those students is usually where you're doing a simultaneous equation, and that ends up making it nasty. All right, I'm just quickly waiting for all the thumbs to go down. And then my last question is, and we may not necessarily get there this evening, but we'll aim for it. Who here is aware of vertical projectile motion being a difficult section because it brings in graphs, and maybe you were not paying good enough attention when you did this section in grade 10 and you did graphs of motion, and therefore graphs is where it all just falls apart because you're looking at it going, yay, I look at the gradient, and you don't know why you're looking at things. A lot of you have become very good at adapting, and therefore you've learned the rules. But when it comes to why you do the rules, that's all lost. Okay, so I'm hoping today that we will at least get through doing the vertical projectile motion, how to do things. I picked 3 past paper questions because I felt that they were, I guess, the first few were relatively easy, and that's why I picked them. There's one that looked pretty nasty. And then if there's time, I'm going to do the graphs of motion as well this evening. So we've got a full hour and a half, which is quite a while for this section. I must warn you before we begin that I teach graphs of motion differently to a large number of people. I overteach it. I'm fully aware of this. So I will teach graphs of motion so that you can, from one graph of motion, draw any other graph of motion. And the reason I do this is I find that if I teach it to you in such a way that you know too much, then when you're asked to do something that's basic and elementary, you can do anything. So please be warned, I do overteach this. I don't want you to panic and go, I've never done this before. It's just a method that I've always found works really well for me, and hence it's a method that I've always used when I teach students. All right. So ladies and gentlemen, just a reminder, today we're going from 7 right the way till 8:30. I do hope you can all stay for the full lesson, because I think we may get right at the end where we start on a new section in preparation for Thursday. Okay, so I'm going to get started straight away by just covering a little bit of the background theory. Please, those of you who've joined a little bit late, my sound for whatever reason is not working this evening. It's just specific to Zoom. So if you have any questions, make sure that you type them. If you shout out, you're not going to be able to unmute yourself. I've specifically left everybody muted because if I can't hear you and you're busy talking, it's going to be in the recording and it's going to be terrible. All right, so we are looking at the section on vertical projectile motion. Now, vertical projectile motion deals with objects that are either thrown up or thrown down or dropped. But the key thing that makes the characteristic of being vertical projectile, first of all, is that it's vertical, straight up, straight down. Okay, so vertical in that direction. The next thing is that we're dealing with the projectile, and there's something very important about a projectile. A projectile is an object, sorry for my writing, it is an object that only has the force of gravity acting on it, or the only force acting on it is gravity. So it only has the force of gravity acting on it. That means that if you were to draw a free body diagram, of that particular object, the only force that it would have on it is its weight downwards, nothing else. So because we're dealing specifically with a projectile, it means that we have to ignore air resistance. So quite often when we're dealing with a section, they'll specifically say, you can ignore air resistance, and there's a part of me that wants to go, I have to ignore air resistance. If they tell you not to ignore air resistance, you're suddenly left in a big pickle because you don't actually know how to deal with it if you do get any air resistance. Hence them saying ignore air resistance is a little bit silly. So please, important thing, projectile motion. This is a projectile because the only force acting on it is gravity. You can also say that the only force acting on it is its own weight. Okay, so there's no upward force due to air resistance. We don't deal with situations where there's something called two-dimensional projectile motion. You don't deal with that. You don't deal with objects that are thrown up and forwards. You only deal with straight up and straight down as per your curriculum. Okay, the next thing when it comes to vertical projectile motion, and some of your teachers are probably going to hate me for telling you this, but I don't believe in changing all of the variables from your normal equations of motion. When I teach this to my students, I find that the more information I give you in terms of different things that are the same, the more complicated things are and the harder it is for you. Whereas I could make your life really easy and say, listen, the variables that you learned in equations of motion don't change. So we're going to be dealing with this from the perspective of equations of motion. Equations of motion have 5 variables that you look at: VI, VF, A, delta T, and delta X. I am fully aware of the fact that your teachers may, in light of being perfectly correct, say that if you're dealing with vertical motion, instead of using A, you should use G because it's the acceleration due to gravity. And instead of using delta X, you should use delta Y because technically the X plane goes left and right, it's horizontal, and your Y plane goes up and down. But I'm telling you right now that we're not going to penalize you for using X instead of Y. And we're not going to penalize you for using A instead of G. So when it comes to this section, I'm going to stick straight forward with those are the equations of motion, the variables for motion, the ones that I've written in blue, and those are the ones that you can use. Now, just a couple of important things. If you go to an IEB school, you may have been taught U, V, A, T, and S. Only if you go to a school that does the International Examination Board IEB exam. If that's the case, then by all means you can use those equations or those variables in the equations that go with them. But for anybody who's writing a CAPS exam, those are outdated and you may not. So IEB students, I know that you're allowed to use U, V, A, T, and S. Everybody else, please don't, okay? It's not on your formula sheet and you're not going to use them. So VI is your initial velocity. VF is your final velocity. And when we talk about initial and final, we're talking about for a portion of a motion. Initial means the beginning of the bit that I care about, and final means the end of the bit that I care about. I can have a ball that I throw in the air. Please, when I throw it in the air, it's technically going up and down. But if I don't draw it going slightly to the right, as in with time, you won't see it going up and down. So when I draw it to the right, it's not actually moving to the right. It's just to show that it goes up and then down, kind of like that, but you'd see it doing this on a page. So I may choose to make the portion of motion that I care about from here to here. Then initial will be the velocity there, and final will be the velocity there. Those arrows are randomly in a direction. But I could also be dealing with from here to here, or any other portion of motion. It doesn't have to be from right at the beginning till right at the end, unless, of course, that's the bit that I care about. My A is my acceleration. And in this case, because you are dealing with vertical projectile motion, and we know that the only force acting on the object is its weight or gravity, you will always use a value of 9.8 meters per second squared for your acceleration. Please, I've got to be careful. always, unless it's actually not under vertical projectile motion at that point. So there's a possibility that it's something and it's got a rocket propulsion system attached to it and that's pushing it up. In that case, it's not necessarily going to have that acceleration or an acceleration at that point. So the 9.8 meters per second squared is specific to when it's acting as a projectile. If it isn't at that exact moment, then maybe you don't use that. T is the time taken. So it's the time taken from where you call your initial point to where you call your final point, and delta x is the displacement. Now, where a lot of people go wrong with this is that they forget that from this list, 4 of the 5 are vectors. Initial velocity, final velocity, acceleration, and displacement are all vectors. That means that you need to consider the direction when you work with it. So I use the following rules to help you with your direction. With our velocities, if I choose to make downwards positive, now this is another thing. Me choosing to make downwards positive is because I chose it, okay? There is no rule that says downwards is positive or upwards is positive. The way that the matric exam memos are set is that the original direction in which the object moves is assumed to be positive, okay? That doesn't mean they won't give you marks if you make it negative, but if you go back and look at the matric past papers that you've possibly gone through, you'll see that if this object starts by moving up, the memo will work with up being positive. If the object is thrown down, the memo will start with down being positive. So up and down being positive is something that you choose or something that you're told. Sometimes they do say make down positive and then you work from that direction, but it is something where you can choose your direction if you want to. So I'm gonna change my mind here. I'm gonna go with up being positive. So my rule with direction here is that if the object is moving up, ooh, that's bad. If it's moving up, then this value will be positive, and if it's moving down, then the velocity will be negative. Please, that could be up or down at any point above or below where it starts from, as long as you've specifically chosen that up is positive. And I recommend draw a little picture on your diagrams so you know which way you're going. With the acceleration, depending on which direction you've gone here I've said up is positive, so therefore my acceleration will be negative. Acceleration in this case, if you're dealing specifically with the object acting as a projectile, it isn't going to change direction. A lot of people get that wrong. They kind of go, if it's moving up, acceleration must be up. If it's moving down, acceleration must be down. That's nonsense. When we're dealing with vertical projectile motion, whether the object is moving up or moving down, the acceleration is always down. I'm just going to actually write that because it's that important. Acceleration due to gravity, which is what you'll be dealing with in vertical projectile motion, is always, 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 no exceptions, always downwards. Even if the object is moving upwards, it's downwards. Okay. Then we come to our time, which doesn't need a direction because it's a scalar. And lastly, we finish off with displacement. Now, displacement works a little bit differently to velocity. Displacement, what we do is we look at the position where it started. So we're going to take this at a height of 0. Anything that is above here, so above the starting point, we would have a positive displacement, and below the starting point, or technically a downwards movement, would be negative. So I'm going to say above the specific starting point. So if it's overall moved upwards, okay, so starting here, moving upwards, then it's going to be positive. And if it is below the starting point, then it is going to be negative. Okay, so that's just a little bit of background information with regards to what we're looking at, and why it's so important. I find when I deal with these questions, my students probably laugh at me with this, but I always write out what I call a shopping list. I write out every one of those variables and I try to figure out what I've got and what I'm missing. And the reason I try to figure out what I've got and what I'm missing is that will help you determine which of the equations you're going to use. All right, ladies and gentlemen, can I ask you quickly to take a screenshot of all the information that's here? The next thing I'm going to do is I'm going to go through the equations with you and tell you how to decide which of the equations you're going to use. Because it isn't a multiple guess, there is a very clear rule as to what you use where. So, VI, VF, A, delta T, and delta X. We have got 4 equations of motion that are given on your formula sheet. Please note, unlike Newton's laws, there isn't a specific number for any of them. So it isn't like one's equation of motion number 2 and it's a specific thing. So VF is equal to VI. Just give me a sec. Thank you. VF is VI plus A delta T. VF squared is equal to VI squared plus 2A delta X. Delta X is equal to VI delta T plus a half A delta T squared, and delta X is equal to VI plus VF over 2 times delta T. Now please note there's slightly different versions. I in fact can show you, I've got the copy of the exact one, where are we? The exact one on the formula sheet over here. So I'm just quickly going to share it across so that you can see the formula sheet. Okay, so here is the actual formula sheet that you get, and I think I got this from the November 2014 paper. So it's just randomly from any one of the formula sheets. So you can see all of the different formulae are there. Just a quick note on this. I hope everybody can see the screen. If you can't, you must just shout now, because remember, well, type, then I'll be able to know. I find that when I do these, I completely ignore anything with the Y. If you look at the difference between those two, one's got an X, one's got a Y. It's a whole bunch of extra stress for you to think about Ys. So I tend, when I do this formula sheet, to only view those 4 equations as being my equations of motion. All right, so I'm going to go back to my whiteboard. Okay, and now we're going to discuss how do you pick which equation you're going to use. Quite simply, if you look at these 5 variables that you can use for equations of motion, in every one of these equations, we use 4 variables. In order to use an equation of motion, you need to know 3 things, be looking for 1, and the 4th you either don't know or you don't care about it because you're not going to use it. So what I do is at the beginning of every question, I try to fill in this list of what do I know, and then from there I go across and I pick the equation by what I don't have and I don't care about. So over here, if you look at this first equation, the first equation has got no delta X. So if I don't have the displacement, I'm not looking for the displacement, I'll pick that equation. If you look at the second equation, there's no delta T. So if you don't know anything about the time and it's not what you're looking for, you pick that equation. Okay, over here, if you look at that equation, there's no final velocity. And with this equation, there's no acceleration. Now, those of you that are smart may actually be looking at this already and saying, well, surely if you look at all of those, there's no equation that doesn't involve VI. So some of you might assume that you can't do an equation without VI. There is an equation that looks almost identical to this one over here. I'm going to write it down, but please, you can't use it because it's not on your formula sheet. And that is the delta X is equal to VF delta T minus a half A delta T squared. I mention this purely because I've seen 1 or 2 past papers where every now and again something comes in, and knowing this helps you to answer it faster. So you'll see that the only difference is instead of us starting from the initial velocity, we start from the final velocity, and instead of us adding, we subtract. Okay, but this one here is not on the formula sheet, and hence you're usually not going to use it. I just know that I used it once. I think it was doing a graphs question or something on multiple choice, and it became more useful to know this information than it did to know that. Okay, so what you don't have is going to determine which equation you use. All right, the next thing we need to look at is the hidden information. So sometimes they hide information in your graphs of motion, not graphs of motion, in your vertical projectile motion, where there's something that you should know, but nobody says it because you're supposed to know it already. The first thing is, if they ever use the terminology drop, you must know that your initial velocity is 0 meters per second, provided that it is dropped from a stationary position. Okay. All right, that is an A. Okay, so provided it's dropped from a stationary position. So if I'm on the top of the roof and I drop something, its initial velocity is 0 meters per second. However, if I'm in a hot air balloon rising upwards at 2 meters per second and I drop something, that something starts at 2 meters per second. All right, so if you're in an object that's moving upwards or downwards at a constant velocity, the initial velocity of the object that's dropped will then be moving as if it were attached to you and part of you. The next thing that a lot of people don't seem to get is if I were to draw an object and it's moving up. So please, I'm drawing this ball as if it's moving in an arc. Okay, well, I probably should have drawn that a little bit neater. I'll move it in just a second. So if I draw this object as if it's moving up and then moving down, please don't confuse it. It's moving straight up and straight down, but this is usually how we draw it. What's important for you to realize is that everywhere on this motion, while it's moving up and while it's coming back down, its acceleration is downwards. Initially, it will have a very fast velocity upwards, which gets smaller and smaller. At the highest point in its motion, the velocity is 0 meters per second. It will then move downwards, going faster and faster and faster. Okay, so the most important thing here probably is that at the highest point in its motion or above the ground, the velocity of an object is 0 meters per second. You can almost view it as having temporarily stopped. It moves up and then it moves down. Another way that you could think of this is that its velocity goes, say we said that upwards was positive, its velocity goes from being positive to being negative, and the only way that it can go from being positive to being negative is briefly going through a zero. Very importantly, at the highest point in its motion, while its velocity is 0 meters per second, its acceleration is still 9.8 meters per second squared downwards. No exceptions. All right. So there's another question saying, ma'am, would the velocity as it goes into the air being the same as when it's about to hit the ground? Seb, I understand what you mean with your question, but I'm going to correct you. It's not necessarily. At the same height above the ground, the velocity will have the same magnitude. So if you threw the ball from the ground, when it returned to the ground, it would have the same velocity. But if I threw it from the top of a building and it went up and then hit the ground at the bottom, the answer is no. So I understand that you meant it from, you throw it from the ground, it comes back to the ground. The important thing here is if this is traveling upwards at maybe 1 meter per second, up, when it comes down past the same height, it'll be traveling at the same velocity, but in the opposite direction. So I should rather say the same speed or the same magnitude. Okay, so you may find over here it's 3 meters per second up. That should be a 1 there, and then up. This will be 3 meters per second down. All right, so sometimes they don't tell you these things, they just assume that you should know them. The other thing that comes in that's very useful to know is that from a certain position, the amount of time it takes to go to the top is the same as the amount of time that it takes to return back. So if we were to say that this has a certain time delta t from here to here, will be the exact same amount of time to return back down. You can actually plug things into one of the equations of motion and prove that by just saying, here we're going from initial velocity is 3 up to 0, and then from 0 to 3 will take the same amount of time both ways. All right, ladies and gentlemen, that is as far as I go with the theory. I'm going to repeat that at every point in this motion, the acceleration was 9.8 meters per second squared downwards. I promise you, some of you are going to, without doubt, at some point get confused and say, oh, but it's moving up, so it must accelerate up, or the silly one, at the highest point in its motion, its acceleration is 0. Just to quickly counteract that, if an object has 0 acceleration, it is stationary or traveling at a constant velocity. So I often tell my students, imagine you threw a ball into the air, and at the highest point of its motion, it's had 0 acceleration. Has anyone ever thrown a ball into the air and it goes to the highest point and then it stops? It just stops and just stays there. It doesn't happen. What happens is it gets to the highest point of the motion, slows down, and then comes down. So the idea of how the acceleration is always downwards is the acceleration being downwards is what slows this velocity from being a big upwards to a smaller upwards, and stop. The acceleration being downwards is what takes it from being a stop, stationary, to downwards a little bit, downwards faster, and downwards very fast. So at all points in the motion, it is accelerating downwards due to the acceleration due to gravity. All right, before I move on to the questions that I've set aside for us to do today, does anyone have any questions, or are you prepared for us to just jump in and then see when we had questions what they are? All right, so I'm going to clear everything and I'm going to go back to sharing my screen. There we go, not that one. To sharing my screen was this one. Oh, there we go. All right, so I've set aside a couple of questions. I'm not necessarily going to refer back to the set of equations of motion. I do know most of them relatively well, but if you don't, by all means, you can quickly take a screenshot so that you've got a picture of that to be able to use in just a second when we scroll down. Okay, all right, so I'm going to try and see if I can scroll down to just below it without losing it. Sorry, sometimes it takes me a while to get to the right place. Okay, so here's our question. We're told that an object is released from rest from point X. As soon as I see that released from rest, I add in on my diagram that the initial velocity is 0 meters per second there. From above the ground as shown in the diagram below, it travels the last 30 meters in 1.5 seconds. Before hitting the ground, ignore the effects of air friction. Ignoring the effects of air friction is important for any type of vertical projectile motion. All right, so the question here says, name the type of motion described above. And I actually skipped this a little bit. I told you what a projectile was, and that a projectile is an object where the only force acting on it is gravity. I'm now about to add to that. The type of motion, the object is the projectile. The type of motion, there are two ways that we can describe the motion. We can either call it free fall, or we can call it vertical projectile motion. There is no difference. Okay, so you're allowed to refer to free fall and vertical projectile motion as the same thing. The difference is that a projectile is the object where the only force acting on it is that of its own weight or gravity. Whereas the type of motion is the motion of an object where the only force acting on it is gravity or its own weight. You may choose whether you describe it as gravity or weight. Okay, so assuming some of you have got this already, I'm going to give you a chance to answer some of the questions, but we're going to get started. Question 3.2, 3.2.1, calculate the magnitude of the velocity of the object at point B. Now, this question is not very difficult. It is exceptionally difficult if you have got your mind set on going from there to there. If you're insistent that you're going to go from there to there, let's look at what we've got. VI, VF, A, delta T, and delta X. In this case, We've got an initial velocity of 0 meters per second. We do not know how fast we're going at B. We know, let's go and assume here that since it's moving downwards, our downwards is going to be positive. We know our acceleration is 9,8 meters per second squared. We don't know the time and we don't know the distance. Do you remember right at the beginning I told you you needed to know 3 things? We only know 2, so you cannot go from X to B. That's going to waste your time and you're not going to get anywhere. So instead, VI, VF, A, delta T, delta X. Some of you hopefully will start writing this out. I find that it makes such a difference to being able to answer these. I'm now going to go from B to the ground. Okay, so if I go from B to the ground, I don't know my initial velocity. Okay, but it's what we're looking for. So I'm not going to put it in as a cross, I'm going to put it in as a question mark. Okay, so here technically the final velocity would have been what I was looking for. Now it's the initial. Do you understand that from X to B, that is your initial and B would be your final? If you're going from B to C, that is your initial and that is your final. So what's initial and what's final is a perspective depending on where you're viewing yourself as starting from. Our final velocity, we don't know how hard it hits the ground. Please do not ever tell me that it hits the ground traveling at 0 meters per second. That would be amazing. I always threaten my students. You'll notice I'm a little bit violent sometimes as a teacher. When you say things like it hits the ground with no velocity, I go and say, do you want to go and lie in the car park? And I will throw things off the balcony at you and they'll hit you with no velocity. It's not going to happen. If something hits you and it's fallen down, it will hit you with a velocity. So just imagine if something hit you with no velocity, it wouldn't hurt. In fact, it wouldn't even really hit you. It just kind of land on you and not touch you. Okay, that's rubbish. Doesn't happen. All right. Our acceleration here is 9,8 meters per second squared. The time taken is 1,5 seconds, and the displacement is 30 meters. Now let's consider our direction. From B to C, it's 30 meters down. Positive is down, so that's positive, and we're looking for VF. All right. Can I quickly just ask while we're on this, who would have already been able to do that but by themselves? Thumbs up if you're able to do all of that but on your own and you'd have sorted it out. Fantastic. Got to be careful about how quickly I ask questions. All right. Okay. Hands down, hands down, hands down. Next question. Who feels that they might have gotten confused because they were so dependent or so keen to go the first bit that they didn't consider that they could do something later on? You can be honest, it's okay. So what you've got to consider here is that sometimes what you want to do isn't going to be what you're able to do, okay? I can tell you right now, there's no way I could have gone from here to here. As much as I wanted to, it's not going to work. All that I'll do is I'll end up getting frustrated. So please just bear in mind that if you ever ask the velocity at a point, that you can often do it from the top or the bottom, and one of them may not work. So you've got to be prepared to be adaptable. The next thing is our equation that we're going to use here is the equation without VF, and that's delta X is equal to VI delta T plus a half A delta T squared. I'm going to tell you this, and today I'm hopefully not going to mess it up. The squared is where most people mess up on this one. Also be very cautious. If you ended up with a 0 for any one of your values, please sub it in. I know it's very easy to go, oh, but I know if it's times by 0, everything disappears. Unfortunately, you lose your substitution mark if you leave off a 0, even if we know just as well as you do that multiplying something by 0 gives you 0. So over here, my displacement is 30 is equal to VI multiplied by 1.5 plus a half 9.8 times by 1.5 squared. So it's going to be 30 minus a half times 9.8 times 1.5 squared. You may take as many steps as you need to do this. Let's just check I get that right. 30 minus a half times by 9.8 times by 1.5 squared. Okay, and then I'm going to take that across and divide by 1.5. Hoping I didn't mess up anywhere. I got that the initial velocity is 12,65 meters per second. Okay, Just double checking here. I'm sure that none of you guys would have spoken up by now if my maths was off in the evening, but I always have to be careful. Yep, that works. All right, so that would be the answer. Now, please, the use of the word magnitude tells me that I'm treating it, although I've got to this answer, I don't have to put in the direction, so I could write 12.65 meters per second. If you do put in a direction when you're asked for magnitude, usually the assumption is when marking that they ignore it rather than penalize you for it. Okay, so if you're asked for magnitude and you do give extra information, it's unlikely to count against you. All right, so that's the first question. The second question is the height of X above the ground. So we now know what B is. So I'm going to go back and I'm going to use the information that I started with right at the beginning. I may choose to do other things, like it may get a little bit confusing. If you look at this is 5 marks, so it isn't very straightforward. I could try and work from X to the ground, but the problem is I don't know this distance or this time. So instead what I'm going to do is I'm going to work out the distance from X to B and then add it to 30 and I'll get to my answer. So if I now jump into this question, let's see what else we've now got, because we did a little bit of working out. We've got that the final velocity from X to B is 12.65 meters per second. We are not looking for the time, we're looking for the displacement. So from here, we're now able to do it because you've got your 3 looking for a 4th. Sometimes knowing that you always need to get the 3 to look for a 4th makes it very easy for you to know whether or not you've got enough information. So over here, the equation that we've got is the one without t. So we're going to say VF squared is VI squared plus 2a delta x. Final velocity is going to be 12.65 squared. My initial is going to be 0 squared plus 2 times 9.8 times delta x. Please, very importantly, if you had got the wrong answer here and you substituted it in there, you should be able to get every one of your 5 marks. This is very important because a lot of people lose out on marks. They can't solve the first problem, so they throw away 9 marks. My advice to my students is if you can't solve the first problem, write at the end and go, wow, the velocity was 3 meters per second. Pick a number, any number, but write in a value there so that you can still get the marks for the second part. Okay, so as long as you have got an official value that you got for this, even if I cannot see how you got it or where you got it from, if you used it in the subsequent step, you cannot be penalized at all for using it and using it correctly. It's just a little bit of a, it's not even a cheat, but it's a tactic to make sure that you don't throw away exam marks. Because a large number of people, if they can't do question 4, they throw away all 5 for the next one, whereas you can just write anything you want and then use it in the next step and keep all of your marks. It's a sneaky thing, but it really works well. Okay, so my 12.65 squared, don't forget you do put in your 0 here. That value divided by 2 divided by 9.8 gives me that my delta x is 8.16 meters. Now it's very important that you show when you're working out that you understand that there is a difference between the height and this displacement. So don't now go and call this delta x again and then say delta x is 8.16 plus 30. That's missing the point. Give them different names that it's clear that they're different things. So over here I'd say h is equal to 8.16 plus the 30. Okay, so height is a common thing that you can use that's nice and neat. And that gives me an answer of 38.16 meters. All right, I hope that that makes good sense. So that was the height above the ground. Now, actually, they told us that it was x, so maybe instead of using height, I could say x equals. Okay, but height x, they'd figure out what you were talking about. Just be careful, though. Maybe go back and change that into an x, but not a delta x. Delta x is our displacement. All right, does that make sense to everybody? Okay, I'm just going to quickly stop sharing. Okay, can I quickly ask, everybody getting sense from this? Is it working? Okay, good. Okay, good. I'm going to wait again until all your hands go down. Sometimes when your hands are up, I've got to wait. All right, next question. Probably more important. Who does it make more sense to than it did before? Because that's probably a more important question than does it make sense? Okay, some of you. No, that's wonderful. Okay. All right, just quickly, there was a question here. Why is the 9.8 meters per second squared not negative? It's because I chose to make downwards positive, because right at the beginning, the object was moving downwards. So I chose to make downwards positive because the object was released from rest at X and went downwards. So down is positive, and the acceleration due to gravity is always downwards. So that's why I chose to work in that particular direction. All right. I unfortunately did cut off the rest of this question here because it went on to graphs, and I didn't want to go into graphs, and I don't want that page up either. Okay, so let's move on to the next question here. All right, so now we're going to give you a little bit more of a chance to get involved and to actually try and do some of the questions yourself. I tend to find that the more you do in these lessons, the more you remember how to do things, especially if you still get the solutions afterwards. So we're now told that a ball A is thrown vertically upwards. Please bear in mind, if it is initially upwards, then I'm going to, in this case, choose to make upwards positive. That may mean that if it goes down below here, that its displacement actually becomes negative. So anywhere below here, I deal with the displacement that is negative. So we show it's negative that way. And anywhere above here, the displacement is positive. Just something to think about. Also, anywhere where it is moving upwards would be taken as positive. Anywhere where it is moving downwards would be taken as negative, even if it were moving up or down. So this applies whether these are here or here. So it's not to do with whether it's above or below the starting point. It's at all points. Moving up, velocity is positive. Moving down, velocity is negative. All right, so let's go through the information. So it is thrown vertically upwards at 15 meters per second from a height h above the ground. Quite often they make this be on a cliff or the top of a tall building or something like that. And at the same instant, a second ball B is dropped from the same height. Once again, remember what I've told you about the word dropped. Okay? Both balls undergo free fall and eventually hit the ground. So eventually hit the ground, they haven't told you that they hit the ground at the same time. So first question asks you to explain the term free fall. Now, I'm not going to ask you to do this just yet, but you've got to remember that free fall has to do with the motion. So I'm not going to require you all to write it down. I am going to give you the answer here, but it is the motion of an object acting under only the force of gravity. You've got to clearly indicate that you understand that it's motion and then that the object has only one force. You can't say just acting under the force of gravity. I'd say make sure that it's very clear in your wording that it's only gravity or just its weight or no other force but gravity, something like that. All right, ladies and gentlemen, now's where you've got to start thinking. I want you to work out the time it takes for ball A to return to its starting point. So that's for ball A to go from here up, back down to that point. All right, so I'm going to quickly undo where that little drawing was. I'm going to pause sharing my screen, and I'm going to encourage all of you to try and do the working out as well, and then I'm going to go through the solutions with you. All right, please get started on that right now. Okay, please note that with this information, you actually have a number of different equations you can use. So there isn't just one, there are many different versions. Okay, I'm going to ask that as soon as you've got your solution, you quickly give me a thumbs up so that I can see who's got the answer. Okay, good. All right, that looked like the majority of you, and I don't want to keep us on this for too long. I'd very much like to be able to get to the graphs of motion this evening. So just to give you an idea as to how I solved this, and I hope I didn't make any mistakes in my calculation, but I assumed that upwards was positive because that's the initial direction that we move in. So my initial velocity was 15 meters per second. I mentioned to you that when the ball comes back past the same height vertically above the ground, it will be traveling at the same velocity, but in the opposite direction. When it reaches B, it's traveling downwards. The acceleration is negative 9.8 meters per second squared because acceleration is downwards, up is positive. We're looking for the time. Also, if you're smart and you think about it, if it goes up and comes back to the exact same height, its displacement is 0 meters. Now, you've got to be a little bit careful. I think there's one of the equations of motion where they end up canceling both sides because you get 0 equals 0, and then you can't actually solve for the time. So just be aware of the fact that if you do pick that one, you may have to try again. I went with the equation VF is VI plus A delta T. I had negative 15 is 15 plus A times delta T. I ended up with negative 30 when the 15 went across, and I ended up with 3.06 seconds. Can I double check? Did everybody get the same? Okay, that's a good sign. Awesome, well done. The next thing is that if I'd asked you how long did it take to get to the highest point, I wouldn't need to redo this if I've already done this, but if I divide that value by 2, I can see that it would take 1,53 seconds to get from A to the highest point and 1,53 seconds to get back down to there. So that's just a little saving time tip if you need to save time. All right. Then we've got a question, and this is probably the harder of the questions. As soon as something's worth 6 marks or more, I tend to find that you've got to think a bit. You are asked to work out the distance between ball A and ball B when ball A is at its maximum height. Okay, so I would say here, since we're working out the distance between them, my logical thing would be to work out what is the height or the maximum height that ball A reaches. So I'd know how high ball A was at. And then I'd have to work out the amount of time it took ball A to reach the highest point. Nudge, nudge, wink, wink. I may have told you how to do that already in one mark's worth of effort. In that amount of time, how far down does ball B fall? And then what is the distance between them? Let's pretend that ball B has fallen to here. What is the distance between them? That would be my answer. So those are the steps that I would take. Before I throw you all into the deep end, can I quickly ask who thinks that they could solve this completely on their own at this point? Okay, good. Good, good, good. So, ladies and gentlemen, I'm going to give you a chance to solve it on your own and prove yourselves right, which is wonderful. So I'm going to pause sharing my screen so that I can do the same calculation at the same time as you. It's 7 marks worth. It should take you a little bit of time. Please don't panic. Just keep working. All right. right, ladies and gentlemen, if you've already got an answer, just give me a thumbs up. If you haven't, don't panic. I'm not going to race you. Okay, well done. Okay, now I just want to, while you're still busy working, point out a couple of things that I've found over the years that I hope nobody takes offense at these. This may apply to some of you, but I've had some students in the past who've said to me, ma'am, I can't work out acceleration because none of the formulas start with acceleration. You please need to note that it's very unlikely that the thing that you're looking for, the variable that you're looking for, is the subject of the formula. You need to be comfortable with rearranging formulas. Also, and this example is one of the cases, you may find in this example, if you've done it correctly, that the difference between the distance that ball A moves up and ball B moves down, they look like they're the same number. If you've done it right, that's okay. There is no rule that says that, okay? There is absolutely no rule. So please don't work on a basis that if one's gone up a certain amount, the other must go down a certain amount. It depends on the velocities that they're thrown with. It depends on all sorts of other things that you cannot turn it into a rule. Okay, students quite often are very good at seeing things and going, oh, wow, I can see that, and then turning it into a rule, and there is no rule. Okay, I promise you, if it's that easy and if there is a real rule, I will tell you the cheat. Because if it's legal and will get you full marks, I'm never not going to tell you how to do it the easy way. But in this case, there is no such rule. Okay. Ladies and gentlemen, I think most of you should have had enough time to do this. So I'm going to quickly run through what I did. I hope, in fact, let's just quickly start. Who got to an answer of 22.95 meters? Okay, good. No, that's a good sign. I always have to start checking because as we hit into the late evenings, my maths tends to fall apart a bit. So what you'll see over here was that I did from A to the highest point. And I said that it starts at 15 meters per second, it ends at 0 meters per second. My acceleration is negative 9.8 meters per second squared down. Up, 0 doesn't matter. Acceleration's down, so it's negative. I could even have used the time of 1.53 seconds and managed to get to the same answer using a different equation of motion. So this information went in here for me to work out that the distance that ball A traveled upwards was 11.48 meters. Then I used this time being a half of the 3.05. I used that time into my new set of equations of motion, which was for ball B being dropped and falling down. Remember that B was dropped. Okay. All right, please don't worry, Rebecca. The question was about distance. So because it was about distance, Rebecca's question was that she managed to get a negative. So don't stress at all with getting a negative. With this being a distance, what I did here was I didn't think of this algebraically at all. I worked out that this was positive because it was up. This was negative because it was down. But my question being about distance, I literally viewed this distance as being 11.48 there, and this distance here that I've done over there as being 11.47, and I viewed them both as being distances, so I didn't bother with the direction, specifically because it's distance. There'll usually be distance or height. We can't deal with the displacement between two objects because displacement is from your starting point to your finishing point, not the distance between two things. So that's why you had to think of it that way. I must be honest, I think if you ended up with an answer of negative 22.95, they may be prepared to ignore the negative, but there's a part of us as physics teachers that would go, what does she think the negative's meaning? And then somebody may say, well, we've got to penalize that because it can't mean anything or something silly like that. So I'd just be cautious that you make sure that you understand that bit. All right, Rebecca, does that make sense to you? You can just give me a yes. Okay, because I know at the moment I can't hear anybody, so I've got to double check it. All right, so hopefully this made a lot more sense to everybody. Okay, so I'm going to quickly clear. Today I got a bit too excited and I forgot to give you guys your stretch break. So I'm going to suggest just quickly, sorry, those of you who, we've got quite a couple of people who are just starting today for the first time. We usually at 45 minutes in, I suggest to everybody that you stand up and you stretch your legs, because some of you will otherwise be falling asleep on me. So quickly just stand up, get a little bit of a stretch in there. Make sure that you don't fall asleep later. Okay. Sometimes I remember at 45 minutes. Sometimes I'm so into it that I forget. All right. So, ladies and gentlemen, we have a choice at this point, and I'm going to rely on you actually voting for it. So, our choice is either that I can carry on practicing. I guess I've got a slightly more tricky example of the vertical projectile motion questions, or we can spend the last half hour with me teaching you how to do graphs of motion as I teach them to my grade 10s. So I'm just quickly changing so that I can see all of you. Okay, first of all, you've got your two options. Option 1 is going to be doing one more question that's harder. Option 2 is going to be doing how to do graphs of motion and the full theory of graphs of motion. So if you would like me to do the hard question, quickly put up your thumbs up now. Okay. Okay. All right. It looks like a lot of you. I hope this isn't going to be one of those nasty ones where it's so even that I've got to make the call. And then the other option is for us to do graphs of motion. So who would really like to jump onto graphs of motion? Okay. Sorry. Just a quick thing. If we don't do graphs of motion today, we will definitely do it on Thursday. So you don't need to panic. Okay. Graphs of motion, I'm really sorry. You guys have been horribly outvoted. So I'm going to do the trickier question now. I have to breathe in and out because I think the one that I've chosen is one that scares me a little bit too, because I didn't check through how to do it before we started today, but I do know that it's a nasty one, or at least I assume it's a nasty one. Okay, so we have got a nasty question here. Hopefully it will live up to expectations and I won't incorrectly have gone and sold you guys false information, but I suspect this is a nasty one. So we have ball A is dropped from the top of an 80-meter high building. 1 second later, another identical ball B is projected vertically downwards. As soon as we use the word projected, we're meaning that it's thrown downwards with a speed of 14 meters per second. So I'm just going to quickly write in here that this is 0 meters per second so that I don't forget. Okay. As shown in the diagram below, and you're asked to ignore the effects of friction. Now, I actually want to do an experiment for you. So I'm going to ask my child if you can quickly get me a piece of paper and then a hardcover book. Just look through there. Okay. Something that's very important for all of you to know is that an object will fall at the same acceleration regardless of its own mass. I need a book that's the same size as the piece of paper. Okay, this one at the bottom. So I'm going to quickly zoom out a little bit on myself and we're going to do an experiment. If you want, I strongly suggest you do the same experiment at home because it's a really cool one to do. Okay, I've never tried filming myself doing this, so it's going to be a little bit interesting. You're going to have to trust me on the results. Okay, so imagine that I took a piece of paper and a book and I dropped them from the, I'm just going to look up while I do this. You guys are going to get dizzy. And I were to drop these from the same height above my table. Which one, sorry, I'll come back to this question in a second. Which one's going to hit the table first? Book or paper? Okay, you're going to have to type here very quickly. Actually, let's do this very easy. If you think the answer is book, give me a thumbs up. Who thinks it's book? Okay, so if I drop them both, you're correct. Now, you're going to have to do this at home because it really doesn't work with this distance. Let's quickly see if I can unplug there and get me a bit more wriggle room. Okay, you're not even going to see the table there. What about if I did it again? Who's going for book again? Who's going for book again? They hit at the same time. Now, this last one's the really cool one. What about if I do it this way around? Most of you don't realize it, but if you put a piece of paper on top of a book, the only thing that's making them fall at different speeds is our air resistance, okay? So I strongly suggest, I know most of you couldn't see that, But what I did was I dropped them next to each other, and the book fell considerably faster than the paper because of air resistance. We ignore air resistance in vertical projectile motion. If you put your paper underneath the book, most of you think that it's the weight of the book that makes them fall at the same speed. But if you take that piece of paper and put it on top of the book, the piece of paper uses or gets rid of its air resistance because the book moves through it first, and they still hit at the same time. Okay, that was just a quick, sorry, interrupting myself. Who found that interesting? I hope all of you managed to vaguely see what I was trying to show you. It works way better in a classroom where you're actually like there. Okay, cool. So let's go back to where we were. You can go and practice that one at home if you found it interesting. Okay, so let's go back to this. Sorry, it just jumped at the second and I had to do it. How much marks is, okay, now this question unfortunately didn't have marks. It came out of a test that my students at some point were required to do, but I know that it caused them huge issues. So I'd say that a question like this is probably worth about 8 marks in an exam. And what makes it so tricky is that it's completely unscaffolded. So quite often when we want to make your life easy, we give you part question 1, question 2, question 3, question 4, and then we'll have guided you through the steps. Here we kind of throw you in the deep end and say, good luck, solve. Okay, so here ball A was dropped, so its initial velocity is 0 meters per second from the top of an 80-meter high building. 1 second later, now you've got to be very careful. If ball A falls for a time t, ball B is going to be 1 second less, so it's t minus 1. That's where everybody falls apart. If it's less time, you minus the time. If it's more time, you add the time. So just think about that when you're doing a question like this. So that ball B is projected downwards with a speed of 14 meters per second, as shown in the diagram below. Ignore the effects of friction, which you would. Sorry, it was the friction which got me distracted there. Now you're asked to calculate the speed with which ball B is traveling at the instant it passes ball A. All right, so I'm going to start with a quick question here. Who thinks they have an idea as to how to solve this? Who has an idea of how to start? Maybe that's very important. Maybe not all of you know how to solve it, but who knows how to start? Okay, so ladies and gentlemen, I'm going to suggest that you start. I'm going to check in every now and again to tell you what I've done. So I'm not going to do the whole thing without telling you anything, but I'm going to try and set up equations of motion, just so you have an idea. I'm going to assume something maybe like when ball A and B pass each other, let's say that they've both fallen a distance x. They must be at the same height when they pass each other, and since they both started from the same position, they're both going to be a certain distance above the ground. Okay, so my hint, sorry, I'm giving you the hint, is that I'm going to set up an equation for A from when it starts till when it reaches point X, so till it's fallen X meters. I'm going to do the same thing for ball B until it's fallen X meters. I'll then have 2 equations, but you're going to have to be very careful with this because you're going to have 2 variables. You don't know what the times are that either of them have fallen, but you know that one will have fallen 1 second less than the other. So you're going to have a question here where you don't know what X is and you don't know what T is. You also have to be very careful because you probably don't know very much about their velocities at that time either. So before I go straight into it, because I need to think about it, I'm going to quickly stop sharing. I'm going to give you a chance to try and come up with the equations, and then I'm going to run you through the solution in intervals as we get there. All right, so try and see how much you can do in terms of setting up equations of motion for ball A and for ball B. Okay. You can sometimes find it's a lot easier if you write down your VI, VF, A, delta T, delta X, and fill in as much as you can for ball A until it's fallen to distance X, and then the same thing for ball B. Another big hint, make downwards positive. It just makes logical sense. All right, can I ask who so far has managed to figure out just their variables, V, I, V, F, A, delta T, and delta X for both balls? You don't have to have done anything more than figure out your variables. Okay, fantastic. So I'm going to quickly share that with all of you so that we can make sure that you're on the same starting place. Okay, so if you look over here, ball A starts from 0 meters per second. We don't know how fast it's going at this point. Okay, yes, I know that long term, this is what we're trying to solve, but we can't get there in one step. Okay, so we're going to say that we don't actually care how fast either ball A or ball B is traveling when they've fallen X meters. But it starts from rest. We don't know how fast it's going. We know it has an acceleration of 9.8 meters per second squared downwards. We know it falls for a time t. I like to give the first one a time t. You may give the second one a time t, but then this would be t plus 1, and that would be t. I'm letting t be the time that the one ball falls for. Then my displacement is it's going to fall x meters down, and x is positive. So just double check your positive direction. That's positive, positive, positive. We're all good. Ball B is thrown downwards at 14 meters per second, so its initial velocity is 14 meters per second. Its final velocity we don't care about yet, even though I know it's what we're trying to get to. Later we'll come back in and we'll solve for this, but it's not our first thing. We first of all have to work out where they cross each other. Okay? The acceleration is 9.8 meters per second squared. The time it takes, because it was thrown down 1 second later, if this fell for 12 seconds, this would only fall for 11 seconds. So it's 1 second less falling time, and it has to fall the same distance because if they're passing each other, they must have covered the same displacement. Okay, can I quickly have a show of hands who managed to get those variables so far correct? If you did, that's the important bit. Once you've got that, it's good. If you can't get that far, unfortunately, it means that anything that you do after this becomes meaningless because it's going to be wrong. Okay, now what you're going to do is you're going to use an equation which doesn't involve VF to come up with two simultaneous equations. The equation without VF is delta X is equal to VI delta T plus a half A delta T squared. So I'm going to suggest that you plug this information into one version of this graph and then this information into another version of the graph. Later, once you've done those, you'll have two equations. And because both of them have the same x, you can do a simultaneous equation. What you're effectively going to be doing from that is you're going to solve for t. Okay, technically it's t, not even delta t. You're going to solve for the time t. I guess you could solve for t minus 1, but that's one way to do it. All right. Okay. No, just a quick question. Delta t, you're not going to add 1. If it's dropped 1 second later, it's actually got 1 second less time to fall. So its time is less because it was dropped later. All right, I'm going to pause sharing again, and I'm going to put together those two equations myself. Please try and do them as well on your own. I know it's sometimes easier to wait for somebody to do it for you, but that way you don't really understand as much as you could. This is where things come down to maths. Right, ladies and gentlemen, I'm going to quickly share at this point, just in case I've messed up anywhere. It does happen usually as we head into the last little bit of the lesson. So over here, I subbed in initial velocity is 0 times by t plus a half 9.8 times by t squared. Okay, you will never end up getting a negative time because there's no such thing in terms of a negative time. Time has to be positive. Time's a scalar, so you'll never have a negative time to work with. Okay, time has to be positive. By definition, you can't go back in time. Okay, so can I double check? Did everybody get that for their first equation? So x is equal to 4.9 t squared. Okay, some of you did. That's fantastic. And then the next question was a little bit nastier because you had x, same displacement, but now it's 14 times by t minus 1 plus a half times 9.8 times by t minus 1 squared. Please spend some time multiplying this out. I can tell you firsthand, it's where I tend to make my mistakes, and it's definitely where most of you tend to make yours. And then remember to be very careful about multiplying in through your brackets so that you don't mess up. So can I please double check here? Who got 4.9 t squared plus 4.2 t minus 9.1? Just quickly checking, because if most of you did, yay! Okay, that's a good sign. I did too. Good. Now what we're going to do is we're going to equate these two together. We're going to say, listen, x equals x. So therefore, 4.9 t squared is equal to 4.9 t squared plus 4.2 t minus 9,1. Fantastic thing. Those two cancel. So therefore, I get that 4.2 t is equal to 9,1. So 9.1 divided by 4.2, and you'll notice my negatives disappeared because time has to be positive. I got that the time taken was 2,167, so I'm going to call it 2,17 seconds. So that is the time that it takes for ball A and ball, actually that's the time it takes from when ball B, if ball A is dropped. However, it means that the time that ball B falls for is less. So ball B falls for 1.67 seconds. Very important that you remember that however long ball A had to travel for, had time to travel for, ball B falls for slightly less. All right. Okay, so what we now need to do is go into here and work out what that value is. I promised you right at the beginning, although we didn't care about it initially, it's now the focus. We don't care about x at all. So in fact, in this equation, the variable we don't care about is x. Therefore, we're going to use the equation VF is VI plus A delta T. Okay, so our final velocity is what we're looking for. We know that it initially started at 14 meters per second. It's going to have an acceleration of 9.8 meters per second squared. It falls for 1.67 seconds, and that will give us a final velocity of 14 plus 9.8 times 1.67, which gives me a velocity of 30.37 meters per second. All right, ladies and gentlemen, I don't know how many of you managed to get all the way till the end on your own, and I hope I didn't make it a mistake there. Ooh. Yes, sorry. Thank you for correcting me. I don't know how I do this. It's one of my silly things. You take away 1, and I don't know why it suddenly changed to 6, but I obeyed myself very diligently. Okay, Thank you for correcting me. You've got to be very careful with what you write down and how much you believe yourself. Okay. Thank you very much. I'm glad we picked that up. Okay, so it's 14 plus 9.8 times 1.17. Okay, yeah, that turning into 1.67 was just magic. So this gives me an answer of 25,47 meters per second. All right. Okay, so Rebecca's got a question here saying, just give me a second. Can I ask everyone to just wait a second before asking previous new questions, because otherwise I'm going to lose track of where they are. So how did you figure out that I needed to find t instead of the other variable? It was easier. I must be honest, I could have solved for either variable. If I'd solved for the displacement, I could have then put it in over there. I would not have had I could have just put x in there and then solved straight away to get this value. But I think it was looking at these two and realizing that those would just disappear themselves so much faster that made me think that I wanted to solve for x rather than the other variable. So you could do either. So making distance the subject to the formula, okay, just quickly. So Rebecca, I could have done it from either side. I think it's just that when you've done this enough times, you eventually look at a question and it makes logical sense as to what thing you'd do next. If you were to do it the other way around, I don't think it would have penalized you. It just could have been a bit messier. So the important thing here for us to do was to get down to one variable. So when it came to ball B, we didn't have an X that we didn't know and a T that we didn't know. We knew one of the others, so we could solve with three variables. So it could have gone either way. That one just looked easier to me once I'd written out my two equations. Okay, also X was the subject to the formula there, which made it easier to see what I was doing. Okay, so does that quickly make sense as to why I made distance the subject to the formula? It was the equation of motion that I chose, and I specifically chose that equation of motion because I didn't know either of the final velocities. Okay. Okay, then there's a question here. They're asking, okay, cool. Yeah, so it was just about me realizing what I had and where I went from it. Okay, I see most of the other questions have been answered. Thank you so much. All right. Ladies and gentlemen, we've got another 8 minutes left, and I can promise you after this one, I think most of your brains are a little bit strained, so we're not going to be doing another question on it. I hope, though, that this has kind of made you aware of the fact that they're easy questions and they're difficult questions. What makes the difficult questions difficult? Can I just quickly ask everyone to take a screenshot before I finish? And I want to talk to you instead of having this in the way. So I'm going to stop sharing, quickly take a screenshot. Okay, so they're going to sometimes be questions where it's really straightforward. This section, however, often is asked in a rather complicated way. So my advice is that if you get one that's got a simultaneous equation, you'll usually know it's simultaneous because the mark allocation will be quite a lot higher. So if your mark allocation is somewhere in the region of 8 marks or more, you're probably going to do a simultaneous equation. It can be rather challenging and tricky because of that, but I think it's very important to just kind of keep your eye on what you can do. With this particular one, what may make it slightly tricky is that the variable that they asked for wasn't even in what you used for your simultaneous equation, which is why it helps. You'll notice that what I call a shopping list of writing down all of your variables will tell you what you know about both objects and therefore what you can work with for both objects. If you don't know that information and you can't see any link between how the two objects are behaving, then you're going to struggle really hard to be able to answer the questions. All right. So, ladies and gentlemen, can I quickly ask, does anybody have any other questions that I can assist you with? Anybody? Okay. I think we're going to call it a slightly early day. Get a whole extra 5 minutes to go and relax. Thank you so much for coming out on a public holiday. I do know that most of you have got other things, and it's quite, I guess, a little bit of a disruption. But I really do appreciate that you value learning this that much. So thank you very much.